Okay, Forbes and his sprinkler, spinning disc, and right. So let's look at this. He's got the spinning disc on top of this pole. That's 5 meters tall. So what happens here? This is a two-part problem. The first part is that the disc spins. Obviously, well, I've drawn it there, but it spins at some rate omega, which we'll find out in a moment. That is an omega, and these little droplets basically just sort of fall off the edges. And so when the droplets leave, they have no velocity relative to the side of the disk. What that means is when a droplet separates, like right here, it comes out of a hole, it's got the same velocity as the side of the disk where it came out. So that means that they're going to go this way. Okay, so if it flips off, it's going to go that way. If one comes off there, it's going to go this way, etc. And this is how sprinklers work if you look at them closely. So what happens here is this guy is going this way at some velocity v, and it's going in the x direction. So what happens then when you look at the side view is that the guy starts like that and then goes do 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 plop. Okay, so vx there, and then he ends up hitting the ground, right? So, and it's 5 meters down. Okay, so to start with, how fast are they going when they come off? Well, that's pretty easy, right? It's just the speed, the linear speed of the side of the disk, right? So the disk has a diameter of 1 meter, which means r is 0.50 meters, and omega omega is 2 pi over t. So let me just do this over here. Let's see, I'll do red for the disk spinny stuff. So omega is 2 pi over t, and then the x velocity of these things as they come off is going to be equal to omega times the radius of the disk, which is going to be 2 pi r over t. Okay, and if you really want to get that in terms of this diameter here, well, 2r is equal to the diameter, right? So we can just write pi d over t instead. Okay, so there's our initial x velocity, and then how long does it take to go down? So we're just going to use delta y equals, and we know since we have no initial y velocity, I'm going to skip that. Well, no, I'm not. Vy naught times t plus 1/2 acceleration of y t squared. Easier just to do it than to say it, all that. Acceleration of y, of course I'm going x, y. Acceleration of y is negative g. So, and once again, cool people use 10 for g. Okay, so it's going to be negative 10. So I'm going to say delta y, and it goes down 5 meters, right? So negative 5 meters this is 0, and then plus 1/2 times negative 10, so negative 5 times t squared. And you don't have to go to TJ to know that that means t is 1.00 seconds. Okay, so that's how long it takes the thing to fall. And then delta x, which is how far it goes horizontally here, okay, is going to be the x velocity times t, which means it's going to be, well, this is your x velocity here, right? Pi d times t. So let me just see if we can get ourselves a little more space. And whoops, there we go. Okay, so that just means this is going to be delta, delta x is, Vx is pi d over t. No, not that t, sorry. Crap. Okay, there. Pi d over period of the whole thing times the time it takes to fall, which is 1.0 seconds. Okay, actually, I ought to figure this crap out, right? Okay, so pi times d. What's the period of the disk? The disk goes at 60 rpm, so that means your period is, of course, 1.00 seconds. Okay, so that's how long it takes the disk to go around once. And so that's kind of convenient since big T and little t are both 1.0 seconds. They just cancel. D is 1 meter. So delta x is going to be 3.14 meters. And if you did it with 9.8 for g, you probably got like 3.17, something like that. But here's the trick. What the problem asked for was how far away from the base of the pole, at what distance from the bottom of the pole do the droplets land. And so if you think about how this is set up, Let me see if I can get just a wee bit more space down there. Close. All right. So here's your pole. Well, okay. Oh, come on. Here's your pole, and here's the disc. I'm exaggerating the size of the disc, okay? And then a droplet comes off, goes doot, 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 plop. Okay. How far is this from this point? Well, that's 3.14 meters, or 3.17, depending on what you got. But how far is it from the base of the pole, which is right here? So you just have to do this little, this is r, and this is delta x. You just have to do this little Pythagorean theorem thing. That's d, and you'll get d. I think we'll get d like, I don't know, d is a little bit more than 3.2 meters. So I think 3.20 meters, maybe a little bit more. I'm not going to worry about getting exactly, but that just so you understand what we're asking for in the problem. It's a review problem, so as long as you understand it, you're happy.